So welcome to our next lecture on shrinkage methods for regression. We discussed previously regression models, and we will now look at the multiple linear regression model in a little bit more detail, seeing that instead of fitting all p explanatory variables from x1 to xp, we are looking for nested models which only use k instead of all p parameters and finding the relevant parameters for the actual multiple linear regression model. You are probably well aware of several model selection approaches, the most typical one being already implemented in R as part of the summary of the multiple linear regression model is the student's t-test for every single one of the coefficients, which tests basically whether this coefficient is equal to 0 or not equal to 0. And this is done by a separate t-test for each one of our coefficients. The advantage is that it's straightforward, easy to interpret, and it can be done right away with the summary. The big disadvantage of this is that we do not consider how removing, for example, the last of these, infant mortality, which has a p-value of only 0.319, has any effect on the rest of the model, and whether other of these p-values might change if we remove one or several using separate t-tests for each model coefficient. So we disregard any relation between those. Therefore, more sophisticated approaches exist, and these are based on the notion of information criteria. So any type of stepwise model selection which removes the most irrelevant variable in each step is based on some of these information criteria, and there are a lot more than just two here presented now, but we will talk about these as the most relevant ones. The Akaike information criterion is basically -2 times the log likelihood plus 2 times the number of parameters in the model. So we penalize the log likelihood function, which is basically the integration of the data into the model and evaluation how well the data fits this model. And we penalize it by the number of model parameters. So we had Q model parameters before, and this K typically is the number of parameters considered in the model. The more we add, the larger this penalty. The specific equivalent of the AIC for linear regression model is the Mallows CP, which is also provided by different types of software systems. The second most relevant criterion is the Bayesian information criterion. This one is also frequently used. We see that the first part is just identical to what we saw above. It's -2 times the log likelihood. But now the second part changes. We have the ln of n in here instead. So we use the logarithm of the number of observations. And as soon as the number of observations exceeds 7, this BIC will always put a larger penalty on the size of the model than the AIC, and therefore BIC enforces smaller models compared to AIC. So choosing the criterion also is a preference for having larger or smaller models. In R, this is done by the step function, and this one provides us the AIC of each model and then systematically removes step by step model parameters in order to minimize this AIC. So a model which removes this irrelevant variable leads to a smaller AIC than we had with the model we started with. Any other removal of a further variable would increase this AIC, this information criterion, and therefore lead to a worse model than the one we have already. But we are looking for something else. Both of these approaches were first fitting the model and then applying a methodology for selecting which are the relevant parameters. And then once we removed irrelevant parameters, we had to fit the whole model again and obtain now different model parameters. What we are aiming for now is to look at regularized regression approaches where we wish to do the model selection and the fit of the model in one go, both of them influencing one another. Selection influencing the model fit having an influence on which parameters will be selected. So in the end, we wish to shrink all the coefficients of all parameters which are not relevant, basically to zero or close enough to zero in order to remove them from our model and only keep the parameters, the explanatory variables, which are actually important. And the two most well-known methods for shrinkage are rich regression and lasso. Rich regression is based on a similar model formula as we had before. This is this first part in the brackets, the yi minus the beta 0 plus the beta j times xij. This is the linear regression estimate, the least squares estimate. And then there's a second part here, the lambda times sum of beta j squared. This second part is referred to as the penalty part here. And this is where the regularization is happening. And for rich regression, we regularize by wishing to minimize these squared beta coefficients in addition to estimating the least squares estimate. So in this way, we change the least squares estimates through a second part, which is this penalty part. Lambda is a tuning parameter here for the method, and it's also referred to as the shrinkage parameter. If this lambda is 0, basically there is no shrinkage happening, then the whole rich regression will basically be the OLS regression. And as soon as this gets more and more important, the impact of this grows, and we are kind of shrinking all our coefficients to 0. So the larger the lambda, the greater the shrinkage. Always be aware that we start summing here from 1 to p. We always keep out the intercept. The intercept is something we do not wish to shrink out of the model, as we would introduce some bias into our models otherwise and have our residuals of the regression not centered around 0 anymore, which is something we really, really want to avoid. So this is what this rich regression penalty looks like. Basically, we're creating these eclipses, and down here we have this circular penalty, and what we wish to do is to change this ellipse, these Peterhead estimators, ellipse in such a way that we will make this penalty as small as possible and have one of them removed from the whole slope if we do not require it at all in our model. So the rich regression estimator is basically what we had before as the least squares estimator, but in addition to just having x transposed x to the power of -1, x transposed y, we have this part where from the x transposed x, we subtract the lambda times the identity. And this is the regularization part. And because this part is here, we can use this rich regression in scenarios where we could not use OLS regression. So including scenarios where x transposed x itself would not have full rank, and therefore this matrix up here would not have an inverse, and therefore we could not compute the least squares estimator in the first place. This is referred to as the regularization property of the rich regression. It allows us to create some bias, which is included here as opposed to the least squares estimator, but this is stabilizing, and it's also able to deal with dependence in our original data matrix. So as we see, when we get this lambda close to 0, we basically remove all the shrinkage. If we get it closer to infinity, if we increase it more and more, the influence of the shrinkage will be larger and larger. Therefore, all the property and the estimated itself crucially depend on the choice of lambda. And we will select lambda usually using cross-validation, which is why we did this in the previous lecture, as we will need it a lot now for our selection of this relevant lambda auxiliary parameter. So also, it's not a necessary requirement, but it's usually helpful to standardize all the regression parameters, as having different scales will have a lot of impact here for the estimation. As soon as we do this, the beta 0, the intercept which we are estimating, is basically the mean of our y variable. Second algorithm we mentioned is the lasso algorithm. The lasso estimator is similar to the rich regression estimator, based on the least square estimate for regression. And also here we see we have a second part where the regularization is happening. And instead of having the L2 penalty with the rich regression, we have the L1 penalty. We use the absolute values of the beta j, and we want to minimize this sum of absolute values. As we know, absolute values have the large disadvantage that this function is not does not have a continuous derivative, and therefore looking for minima will be a lot more tricky than with L2 penalty. But there are some advantages which we gain from this lasso, and this is that now we can actually have shrinkage to 0. Why? Before you could see that the ellipsoid was not able to read this peak and directly have one of the coefficients become exactly 0. Whereas here we now have the possibility of shrinking one of them to exactly 0, whereas the other direction still remains. And this is the large advantage of lasso. There is more shrinkage happening. We can completely remove coefficients because they actually become 0. Again, this lambda is a crucial parameter, and therefore we have to select it with cross-validation. And we will use lasso for whole groups, but first of all we start off with using it for subset, for selecting single parameter, and this is a special case of the continuous subset selection method. We will also make these, so in this case the constraints become non-linear and they are much more difficult to compute because these derivatives are not continuous anymore. But the shrinkage is better than we had before. In order to see this, we will look at an R example comparing the ridge regression against the lasso. This example is built to have 20 explanatory variables, but only the first 3 of those will be relevant for the y, whereas the other 17 will not be relevant at all. They are completely independent. So the basic linear model in the background would of course fit values for the first 3 of these explanatory values, x1 to x3, whereas all the others have estimated coefficients close to 0, but in almost all cases except for this one where the rounding makes it 0, it's not exactly 0. The ridge regression is now built on this linear model coefficients, but this root sum of the squared coefficients will be the part which will be minimized in addition to the least squares estimation. For this, we will use the GLM net. GLM net is the elastic net estimator for generalized linear models, and ridge regression is a special case of this, and we will later look at how elastic nets are related to the ridge regression and lasso regression in general. So in order to do ridge regression, we use GLM net, the elastic net, and we set this alpha parameter in there to the value of 0. We will talk about the alpha parameter in a little bit more detail in a few minutes. So now it's 0, and this makes it ridge regression. Also, we construct a whole grid of possible lambda values, starting from the largest one, 10 to the power of 10, and decreasing in size up to the smallest one of 10 to the power of -2, with 100 values in this sequence. Similarly to this, we can fit the lasso, also as a special case of this elastic net. For the lasso, we set the alpha parameter to equal to 1. Otherwise, all the rest is identical as before. What we see when we look at specific parameters, in the case of the ridge regression, these look rounded all to be like 0. However, this is a kind of deceiving, because the sum of all those still is non-zero. And this is the sum of all except for the intercept, in case you said, well, it's just the first value, the 2.01, which is driving this. No, they are not 0 exactly, so there's not really shrinkage happening. It's just getting very, very close to 0, because we have a very, very large lambda for this specific parameter value here. Whereas with the lasso estimator, we obtain similar coefficients, but now they are all exactly 0, and also their sum of squared coefficient fit is exactly 0, with the same lambda as we had before with the ridge regression. So this is what it means, that lasso shrinks the irrelevant coefficients really to 0, whereas ridge regression only gets us very, very close to 0. Similarly, again, ridge regression provides less shrinkage than lasso. This is another coefficient. We now have a lambda of 43.287. And for this one, we see that all the coefficients, almost all the coefficients, are not exactly 0. Sorry. Whereas, what happened? And their sum of squared values is also 1 point something, so it's away from 0. The very same thing with the same lambda with lasso provides us with exact zeros in all the positions and really removes this specific one from the model. So it really shrinks down to 0. And at the later stage with ridge regression, we see that now the first 3 coefficients are really far away from 0. All the others are also non-zero, and this sum of squares is already 6.8 something, and we were starting from 7 something at the beginning with the linear regression model. Same position in the lasso estimates, and now we see that only for the relevant ones and a few others which are popping up, these are non-zero, and for all the rest we are exactly 0. Therefore, this sum of squared coefficients is still smaller as it is for the ridge regression. It has to be, because we have exact zeros, but we have somewhat more bias because of that. So what does this look like visually for all our parameters? Here on the x-axis, we have the lambda values increasing from very, very small sizes, 10 to the power of -2, to very large sizes, 10 to the power of 10. And here we see the size of the coefficients, and basically the decrease of these lines and how far away they are from zero and how soon they start becoming zero is how quickly the shrinkage is happening here. So before we were looking at different cross sections through this lambda plot, and we are looking at different values of all these coefficients. And we see here that it takes some time, and in the end, even though parameters get very, very close to zero, it takes some while until they really become non-discernible from zero at all. On the other hand, we have the lasso, and we see that the picture is somewhat different here. The important coefficients, again, are away from zero. And then all the others here, they are getting down to zero. And as soon as something is shrunk to zero, it really drops to exactly zero very, very quickly. Unlike this long way of approximating there, converging towards zero, but not becoming exactly zero. In this way, this lasso is much more efficient at shrinking coefficients and removing irrelevant parameters from the model. Zooming in into the smaller lambda values, we see here again the same picture for Rich. It's really decreasing very, very slowly, and it really takes a lot of time to approximate the zero. Whereas with the lasso, this is happening really quick, and as soon as it gets down, it's not converging very slowly, but it's becoming exactly zero and being removed from the model. So I said we will select lambda through cross-validation, and for this the cv.glmnet function is readily available, which does this cross-validation for us. And here we have again the log lambda values on the x-axis, and on the top of this we see the number of non-zero components and non-zero parameters selected by the respective lambda values. We see up here at some degree, after a certain value of lambda, we will remove basically all the variables from our model. Nothing is relevant anymore except for the intercept as soon as we put enough penalty up here. Whereas here for the two lines, we have either a model with 3 or with 4 components. If we select something below that, we will get larger models with more components, which is not advisable for the lasso. What do these two parameters mean? One of them is minimizing the out-of-sample loss in the cross-validation. This is the lambda.min value. And the second one is the largest lambda value, which is one standard error away from this lambda mean value. Why the largest one? Because this will decrease the model size, making the lambda larger. So this is kind of how far can we go and how small can we make this model. As we can see here with the lambda min, we will still keep 1, 2 additional parameters in here, even 3 even though this is the one which minimizes the out-of-sample loss. Whereas when we take the second one standard error away, we only keep the first three coefficients non-zero, and therefore only the first three parameter values, whereas all the others become zero. We did the automatic model selection in one go, in addition to fitting the model parameters. So in this way, this second choice, the one standard error away, is better for this scenario, since we already know here that nothing except for the first three components will be very important. So let's look at algorithms for implementing the lasso, because you will also look at these algorithms for actually implementing your own lasso method. So there are different ones out there. Most famously known are the shooting algorithm and the coordinate descent algorithm. And we will briefly talk about the ideas behind these algorithms. The coordinate descent algorithm is pretty simple in its idea. It basically solves an optimization problem where we obtain the xi plus 1 depending on all the previous ones which we fitted already, previous coordinates, and now filling in the y which we have, and keeping the old coordinates from one step before, and minimizing this target function. And based on some line search algorithm, we will obtain a sequence of such x0, x1, x2 vectors in higher dimensions, which will lead us closer and closer to where we want to get. Graphically, this means we start from some point. We do this line search, we optimize and obtain the first direction, this y direction, then we again update the second one, the x direction, then again we update the y direction, the x direction, and so on and so forth. And this is why it's called coordinate descent. We go in the direction of the different coordinates and we descend towards the center, in the sense of, as we see here from these topological height lines, until we get at the minimum of this optimization problem. Second algorithm for this is the shooting algorithm. So we can obtain the non-regularized regression estimator, of course, in every case. This is the beta zero hat. And we will use this classical OLS estimator as the starting point for our algorithm to estimate the lasso. And we do this based on two auxiliary parts. First part is the sum, 2 times the sum of the xij squared, sum the whole y's. And the second part is the 2 times the xij times the yi times beta m x plus the beta j xij. Why do we use this? This is basically the residual part, and we use these residuals in combination with the x values. We want to update those two, and for doing this, we require an ancillary function, and this is the soft thresholding function. Basically, this is the sign of the first of the two parameters coming in here times the absolute value of this first minus the second one, And of this second part, we only take the positive part, which means anything which is 0 or less than 0 will be set to 0, and only the positive value remains. Why this? We will use the Cj divided by this Aj as the first part in this soft thresholding function, and the chosen lambda value divided by this Aj as the second part. And using this soft thresholding, we update this beta JM algorithm up, this beta JM value up here in the algorithm, and we will stop this once our beta JM plus 1 minus the beta JM, the increase or divergence of the beta values is smaller than some epsilon threshold, or if we reach a maximum number of predefined iterations. You will implement those two as part of your exercises to try out your own lasso algorithm. So what are problems with this lasso? In high dimensional data sets, we have highly correlated variables, and this means they all operate on the response in a very similar way. And if this is the case, the lasso is known to perform not as well as the ridge regression, because this ridge regression has this part which I showed you up there, where it regularizes the OLS estimation and therefore is better able to deal with highly correlated scenarios. Also, in high dimensional data sets, we have the case that features are structured together, and then it would not make sense to shrink part of one feature but not the rest. And therefore, we will later look at the group-wise lasso, which is a generalization of the original lasso algorithm, for looking at a whole set of parameters instead of just one single part of it. So generalizations of this lasso. The ridge regression approach has a very big step in the high dimensional regression, but lasso is the dominant method nowadays. It's more famous, even though it is far less able to deal with highly correlated scenarios. But the advantage of lasso is that there are a lot of different variants, and also variants which can be used to deal with some of the problems mentioned here. So one variant of both the ridge regression and the lasso is the elastic net. This is the machine learning term for we basically mix the lasso and the ridge regression penalty. What do? We start out with the same thing as we had before. We start out with the OLS estimator, and now at the end we have a part which is a 1 minus alpha times a the beta j squared sums, and the alpha times the summed up absolute values of beta j's. The first part is the ridge regression part, the second part is the lasso part. So, and this alpha is the weight by which we are mixing ridge and lasso. This is the reason why before we were using the GLM-net algorithm and we were using this alpha and setting it to 1 in order to obtain full lasso and setting it to 0 in order to obtain full ridge regression. Any other value in between 1 and 0 will lead us to a real elastic net. What's the advantage? The advantage now is that we are not suffering from this problem that the ellipsoid will not become exactly 0, but we are obtaining partially this advantageous property of the lasso that we can really shrink down to exactly 0. On the other hand, I said that the lasso has problems with highly correlated parameters. We obtain the regularization effect of the ridge regression for dealing with highly correlated scenarios. Therefore, elastic net is really strong with within group correlation. And also, if we keep the alpha less than 1 and the lambda above 0, this will lead to a strictly convex problem, and therefore we have the guarantee that we will obtain a single unique solution. You see it says alpha less than 1. Alpha exactly 1 is the lasso, and this scenario is not strictly convex and not necessarily guaranteed to have this unique solution. So there are plenty of algorithms out there which will solve the elastic net minimization problem. Coordinate descent is the most popular one. There are others as well, and this 0.5 part is basically for the quadratic part and helping, so here, and it's helping us with the optimization. So now, in addition to having this crucial parameter lambda, we also have the crucial parameter alpha, because the alpha is how much lasso and how much ridge regression is in our elastic net. And there are two options. Of course, you can subjectively choose your favorite alpha and just stick with that. Or we do the reasonable computational approach, and if we have no idea what to do, let's just try out different ones, do a cross-validation, and choose which is the most reasonable one. So we will now look at a second example. We build up a data set, and the fourth of our explanatory variables, x1, x3, x4, will be highly correlated to x1. So now we create a scenario where we try to explain something and we have this large correlation in there in order to see how this will affect the ridge and the lasso regression part. The y will only depend on x1 and x2, but remember, x4 is correlated to x1, therefore it will also have an influence here. So the linear model, as I told you, it is an absolute necessity for the linear model to have uncorrelated explanatory variables. This is completely destroyed here. The x4 is masking the effects of the x1 and x2 variable, and basically we cannot find any of those to be significant at all anymore. This is one of the main reasons why you never do a model with correlated variables. So if we are stupid enough, we still put it in our GLM, in our elastic net, and see what's happening. And what is happening with the lasso is that immediately it drops the fourth variable and sets this coefficient to 0. And number 3 stays in there for some while. Number 2 stays in there for some while, and number 1 stays in there the longest until it drops to 0. The ridge regression now is affected by this high correlation between the first and the fourth variable. We see now that the first and the fourth, they are basically here close together with respect to their coefficients, and sooner or later they merge and they are removed, both of them together, or stay in the model, both of them together. So we will not get rid of this masking effect here with the ridge regression. Second and third move independently. As we see as before, it takes a lot longer until this real shrinkage to 0 is happening. Now we wanted to look at elastic nets. So we do alpha 0.5 elastic net, half ridge, half lasso. And we see that this ridge effect here, it still remains, that the fourth variable still has some influence, although it's starting further away. But again, we have this effect that both of them move together. But now we see that the second and the third, they are gotten out of the model much quicker. The shrinkage drops to 0, exactly 0, much quicker than it did before with the elastic net. And as soon as we increase the lasso part, this fourth variable gets closer and closer to 0. Those two here are moving more and more apart. But still, as they are highly correlated, this has an effect, and they are both either removed together or kept in there together. And if we get closer to the ridge, of course, the effect is much closer to what we saw before with the ridge regression. And also we see that it takes much longer until variables actually converge to this 0 and are shrunk to 0. I said before that we have a problem if we have features which have several categories. Basically, this means that we want to have a factor removed either as a whole group of variables or none of them, the categories at all. It just would not make sense to remove single categories of a categorical variable, but not the whole variable. So this will be done by the group-wise lasso algorithm. And instead of just looking at the original estimation, we now have this group-wise algorithm where we have the beta j's of the whole groups combined as sub-vectors, and these are a whole vector which may not be separated. So depending on our lambda, either the entire vector beta j will be 0 or non-zero in a general setting. And if all of our groups consist of single variables anyway, then this whole metric will be anyways the absolute values of the beta j. And this means that the whole problem reduces to the normal lasso problem. So we use in equal penalties for all groups, independent of group size. And therefore, larger groups are more likely to be non-zero. This means just by creating a categorical variable with 10 instead of 2 categories, we make it much less plausible that this one will be shrunk to 0 by this group lasso. Even though if none of the 10 categories have any effect, we would still wish to have it removed. So here the computation is somewhat more sophisticated because we cannot move with each coordinate separately. We will therefore use block coordinates because we have blocks of these groups which are updated together. So for this, we look at our previous example. Similarly to before, we create x1, x2, x3, and we now create 2 factor variables. And out of this, the intercept is relevant, and then the first factor is not relevant, the second factor is, and only the first of our numeric variables will be relevant at all. Looking at this, we see that our factors in the model matrix are encoded in such a way that they are basically becoming columns of zeros and ones. And this is also the reason why we have to group these columns of the zeros and ones together, because the original lasso algorithm treats each of the columns of this model matrix separately and independently, with ignoring completely that this one, and this one belongs to the same first factor variable, and this one, and this one belong all to the same second factor variable. Basically, if we put the whole thing in an ordinary least squares estimate, we see that only the fifth group of the second factor variable and only the first of the numerical variables are relevant in this model, and of course the intercept. And basically this is how we constructed it, and also what we would like to see in lasso. If we put it in the ordinary lasso scenario, we see that lasso immediately shrinks the first few columns, which is the different columns of the first factor variable, and it will keep the 7th and the 8th. One of them is the numerical, the x1, and the other one is this column of the second factor variable. So those two are kept and all the others are shrunk down immediately. Unfortunately, along with this number 7, this column go all the other parts of the second variable, and this is completely ignored here. So instead of the ordinary lasso, we look at the group lasso. The automatic color coding is not really the best option for people with not perfect eyesight. My apologies for that. So we have a kind of purple line which is staying in the model the longest. This one is the numerical variable x1, which is really relevant here. And then we have this somewhat darker violet line. This one is the fifth category of the second categorical variable. And now we see a few other lines of the same dark violet shading. These are the other categories of this second categorical factor variable, the F2. And now all of them have to stay in the model as long as necessary, and only all of them together now become 0. And again, for the first factor variable, we have these blue lines here. All 3 of them are shrunk to 0 jointly and not independently as we've seen before. And here we have the other 2 numerical variables. So this is what the grouping does. It combines the effects of all the separate variables. Also for the group lasso, the lambda is of course of relevance. And similarly, as we've seen before, for the lasso value, we look for the ideal lambda with this cross-validation and look at the minimum cross-validation lambda and 1 standard error away. And in between those 2 are the most reasonable options for lambdas. Now you see we do not have a reasonable absolute number of components which are kept in the model because they are now grouped together, and therefore there are no absolute values up here anymore. These regularization methods by now are really popular because we have a lot of explanatory variables available in a lot of data science scenarios, and therefore any type of method which starts with the name sparse has some kind of shrinkage in the background happening, and therefore sparse version of PCA, of factor analysis, of canonical component analysis, of linear discriminant analysis, clustering, graphical models, all types of sparse things are available. A lot of them also implemented in R, and a lot of them are based on similar notions as the regularization ideas which we're talking about now. To briefly summarize your exercises, so you will write your own lasso function by implementing the shooting algorithm as you've seen it written above. For this, you will choose your own tolerance limit epsilon and your own maximum number of iterations. Choose them reasonably enough in order to have a good enough fit, but to not overload your machine for hours on end. Please be aware that the coefficient is not among the values which we are shrinking. Once you have this, write the function which computes the lasso using this for a whole vector of possible lambda values, and which also returns as a matrix of the coefficients and the corresponding lambda values. And compare this function's performance and output against the lasso implementation from GLMnet, and also perform a tenfold cross-validation for the lasso and use the mean squared error as the performance measure. And again, use this CV-GLMnet function and the same plot as before. And of course, it says use the mean squared error and forget the rest, which is set here. Again, then you implemented this function and now you apply it to data, and the data is the HITAS data from the ISLR package. And you will take the salary variable as response variable and create a model matrix based on all the others in there. As we are putting that in here, we currently do not care about correlation between the explanatory variables. we want to even to see how this is affecting our GLM, our elastic net. So use your own lasso function and either decide which lambda is best, or use again cross-validation, or as you've seen now in the lecture, use a whole set of possible lambdas and select the best of one, and then plot the whole path for the coefficients. The whole path means for all possible values, how until it is removed. So compare your fit then against the lasso implementation from the GLMnet, and now also fit the ridge regression and the least squares regression in comparison. And for all these, compare lasso, ridge, and least squares, the prediction on this data, and decide which of the models, lasso, ridge, and OLS, is performing best with predictions, and interpret how these models and briefly argue their performance. And either as a summary or as an introduction to this last part, what is the actual notion of regularized regression? Summarize it in 2 or 3 sentences. What is the notion of shrinkage and sparseness? And what are ridge regression and lasso regression, and how do they specifically differ? This is basically it. Thank you and good luck with your exercises.